Now we'll come to subsequences. Now suppose we have any sequence, say this sequence 1 by n. Now the terms of the sequence are 1 upon 1, 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5, 1 upon 6, 1 upon 7. Now if we consider another sequence which is 1 upon 3n plus 1. Now this sequence will contain the terms 1 by 4, 1 by 7. All the terms in the second sequence, they are already present in this sequence which is 1 by n. Then we can say this second sequence, it is a subsequence of this given sequence. We can take another sequence which is 1 upon n square. Now it will have 1, it will have 1 upon 2 square, 1 upon 3 square. Now terms of this sequence, they are also present in this 1 by n. So this is another subsequence of 1 by n. Another subsequence could be 1 upon factorial n. So these three are the examples of any subsequence of a given sequence. Now classical definition of subsequence is a sequence kn is called a subsequence of sequence n of positive integers if kn belongs to n and kn is increasing. The sequence bn is a subsequence of sequence an if bn equals akn, where kn is greater than or equal to n and kn is a subsequence of n. So for any sequence un, this subsequence u2n, it represents subsequence of even terms, and this sequence u2n plus 1, it will represent subsequence of odd terms. Now the result which is important here is if bn is a subsequence of an, then if an converges to a, then bn it also converges to same limit a. In other words, we can say if a sequence x of real numbers converges to a real number x, then any subsequence of x will also converge to the same limit x. Now another utility of this result is, suppose for any sequence we have two subsequences, say x1 and x2, and suppose x1 it converges to L1 and x2 it converges to L2, and if L1 is unequal to L2, then we can say the sequence x is not a convergent sequence. Now let us take up an example. Say for example, we are given the sequence an which is minus 1 to the power n, 1 plus 1 upon n square. Now it says find a sequence ank which satisfies ank it approaches 1 as n tends to infinite. Now one such subsequence could be this a to n. Now a to n will have minus 1 to the power 2n and then 1 plus 1 upon 4n square. Now this is 1, so we can write a to n equals 1 plus 1 upon 4n square. Now if we take this limit n tends to infinite, a to n, this value is 1. So this is an example of a subsequence which satisfies ank it approaches 1. Now the next one is find a subsequence amk which satisfies amk equals minus 1. Now if we take this subsequence a 2n plus 1, then we'll get minus 1 into 1 plus 1 upon 2n plus 1 whole square. Now if we take this limit n tends to infinite, we'll get this limit as minus 1. So sequence of even terms, it converges to 1, and sequence of odd terms, it converges to minus 1. Now since two subsequences of a given sequence, they converge to two different limits, that means this entire sequence, it cannot converge to a real number. That is, the sequence an, it is not a convergent sequence. Now here the question is, let xn be a sequence of real numbers such that the sequence x2n and x3n, they converge to limits k and l, then which of the following option is or are correct? Now we consider any subsequence x6n Now the sequence x6n, we can write this as x and then 2 into 3n. So it is a subsequence of x to n. That means limiting value of the sequence will be simply k. Now we can also write this subsequence x6n as x 3 into 2n. That is, it is a subsequence of x3n. And if x3n converges to L, then any subsequence of x3n will also converge to same limit L. So from here we can say this k, it must be equal to L. Now in any case, k must be equal to L. But the sequence itself, it may not be convergent. Say for example, suppose we consider a sequence xn and it is defined as, it is 0 if n is relatively prime to 6 and it is suppose 1 otherwise. Now in this case, this subsequence x to n, it converges to 1, x3n will also converge to 1, but the sequence xn, it will not be a convergent sequence. So answer to this question is k equals L, but the sequence may not converge, and that's your option C. Now question number 21 is, let x1 equals alpha, where mod alpha is less than 1 and it is a real number, and we have defined xn plus 1 as xn if n is odd and xn square if n is even. Now we need to find limit of the sequence xn. Now we are given that x1 is alpha. Now for x2, value of n is 1 and if n is odd, it is equal to x1. So x1 equals x2 and it is equal to alpha. Now for x3, value of n is 2 and if n is 2, it is xn square. So it will be x3 equals x4 equals alpha square. So the sequence will be alpha alpha, alpha square, alpha to the power 4, alpha to the power 4, and it will continue like this. And since alpha lies between -1 and +1, this sequence is a decreasing sequence. So this sequence, it is decreasing, and alpha to the power n, it will lie between 0 and 1. So any xn, it will lie between 0 and 1. So this sequence is decreasing and it is bounded. Now since the sequence is decreasing and bounded, it is a convergent sequence. This limit, it converges. Now we consider subsequence of odd terms, alpha, alpha square, alpha to the power 4, then it will be alpha to the power n, and if we take this limit, n tends to infinite. Now if alpha lies between -1 and +1, then this limit alpha to the power n will be simply 0. In the same way, if we take subsequence of even terms, it will again be alpha, alpha square, alpha to the power 4, again it will converge to 0. Now both the subsequences, they converge to this same limit 0. So the limit of the sequence xn will be simply 0, and that's your option A. Now here the question is, let an be a sequence of real numbers, then this limit n tends to infinite an, it exists if and only if which of the following option is correct. Now suppose we assume that the sequence an, it is a converging sequence and it converges to this limit L. Now we consider these three limits, say limit n tends to infinite a to n, suppose this value is L1, limit n tends to infinite a to n plus 1, this is L2, and limit n tends to infinite a3n, and this is suppose L3. Now we know that if the sequence an, it is a converging sequence and it converges to this limit L, then any subsequence will also converge to the same limit L. So this a2n, a3n plus 1 and a3n, they are all subsequences of this sequence an. From here we can say L1 must be equal to L2 and it must be equal to L3. So if the sequence is convergent, then all the subsequences, they'll converge to the same limit L. Now we'll discuss the case when B implies A. That is, all these three limits, they exist. Now suppose limit n tends to infinite A to n, it converges to L1, and this limit an plus 2, it converges to L2, and suppose L1, it is not equal to L2. Now if we consider the sequence A6n, then A6n, it is a subsequence of A3n, that means it should converge to L3, and A6n, it is also a subsequence of A2n, that means it should converge to L1. So from here we'll get this condition that L1, it must be equal to L3. Now we consider this A 6n plus 3, then A 6n plus 3 is 3 into 2n plus 1, and we can also write this as A 2 into 3n plus 1 plus 1. Now this is subsequence of 3n, so it will converge to L3, and this A 2 into 3n plus 1, it is a subsequence of A2n plus 1, it will converge to L2. So this limit n tends to infinite A3n, it will exist if and only if L1 is equal to L2 and it is equal to L3. And when all the three limits, they are equal, then this limit n tends to infinite an, it will exist. So answer to this question is option C. Now here the question is, let Sn be a sequence of positive real numbers such that Sn equals 1 by 2 Sn minus 1 plus Sn minus 2 for all n, then show that the sequence converges and also find the limit Sn. Now what we'll do is, we'll consider two cases. Case 1, if S1 equals S2. Now if S1 is equal to S2, then in that case S1 must be equal to S2 and it will be equal to S3, S4. Then it will be a constant sequence, and if the sequence is constant, then this sequence, it will converge and it converges to S1. Now we consider the second case when S1, it is unequal to S2. So if S1 is unequal to S2, then either S1 is less than S2 or S1 is greater than S2. So we'll take any general case. We'll assume let S1 is less than S2. Now we find S3. S3 is S1 plus S2 by 2. Now S3 is arithmetic mean of S1 and S2. That means S3 will lie between S1 and S2. So we'll write S1 will be less than S3, which is less than S2. Now S4 is arithmetic mean between S3 and S2. So S4 will lie between S3 and S2. We'll write S1 will be less than S3, will be less than S4, and will be less than S2. So if we continue this pattern, we'll end up getting two subsequences. Subsequence of odd terms where S1 is less than S3, is less than S5, and this second subsequence where S2 is greater than S4, is greater than S6. So this first subsequence is S2n plus 1, and this second subsequence is S2n. Now this first sequence is monotonic increasing sequence, and the second sequence is monotonic decreasing sequence. Now we look at these two sequences. S1 is less than S3, is less than S5, and it will be less than S6, S4, S2. Both the sequences, they lie between S1 and S2. So both these subsequences, they are monotonic, and these two sequences, they are bounded. Now since these two subsequences, they are monotonic and bounded, both of them, they'll converge. Now suppose this first subsequence, it converges to this limit L1, and this second subsequence, it converges to this limit L2. So if n is odd, then we can write L1 equals 1 by 2 L2 plus L1, and from here we can write L1 is equal to L2. If we take n as even also, again we'll end up getting L1 equals L2. So both the subsequences, they converge to same limit, say L. Now from this we can write S3 equals 1 by 2 S1 plus S2, S4 equals 1 by 2 S2 plus S3, S5 is 1 by 2 S3 plus S4, and the same way we can write Sn will be 1 by 2 Sn minus 1 plus Sn minus 2. If we add them all up, on the left hand side we'll get S3 plus S4 up to Sn S1 by 2. Now plus S2 by 2 plus S2 by 2, it will be simply S2. In the same way, it will be S3 plus Sn minus 2 plus 1 by 2 Sn minus 1. Now here S3, S4, all these terms, they'll cancel. So here we'll get Sn plus Sn minus 1 will be equal to S1 by 2 plus S2 plus 1 by 2 Sn minus 1. Or we can write this as Sn plus 1 by 2 Sn minus 1 will be equal to S1 plus 2S2 by 2. Now since the sequence is convergent and it converges to L, so this is L and this is L, we can write 3L by 2 will be equal to S1 plus 2S2 by 2. Now this 2 and 2 will cancel. So this sequence will converge to S1 plus 2S2 by 3. And that is the answer to this question. Now the next question is, if a sequence Sn is defined by Sn equals S upon 1 plus Sn minus 1, where S is greater than 0, S1 is greater than 0, and N is greater than or equal to 2, then show that the sequence converges to a positive root of the equation x square plus x minus s equals 0. Now, if s is greater than 0 and s1 is greater than 0, then any Sn will be greater than 0. Now 1 plus Sn minus 1 will be greater than 1. Then we can write 1 upon 1 plus Sn minus 1 will be less than 1. And if we multiply it with s, we can write s upon 1 plus Sn minus 1 will be less than s. So any Sn will be greater than 0 but less than s. That means this sequence, it is a bounded sequence. Now we'll prove that the sequence is a monotone sequence. Now what we'll do is, we'll find Sn minus Sn minus 2. Now this one will be s upon 1 plus Sn minus 1 minus s upon 1 plus Sn minus 3. Now we can write this as s plus s into Sn minus 3 minus s into Sn minus 1 upon 1 plus Sn minus 1 into 1 plus s n minus 3. Now this s and s will cancel. So we can write Sn minus Sn minus 2 will be equal to S into Sn minus 3 minus Sn minus 1 upon 1 plus Sn minus 1 into 1 plus Sn minus 3. Now we can write this as minus S and then Sn minus 1 minus Sn minus 3 upon 1 plus Sn minus 1 1 plus Sn minus 3. Now we simplify Sn minus 1 minus Sn minus 3, we'll get S square Sn minus 2 minus Sn minus 4 upon 1 plus Sn minus 1 1 plus Sn minus 3 1 plus Sn minus 2 into 1 plus Sn minus 4. Now if we look at this result, Sn minus Sn minus 2, then if this is positive, it will also be positive. In the same way, Sn minus 4, Sn minus 6 will also be positive. Then in that case, the sequence Sn minus Sn minus 2 will be greater than 0. That is, Sn will be greater than Sn minus 2 will be greater than Sn minus 4. This sequence will be monotonic increasing sequence. And if this expression is negative, then all the terms in the series, they will be negative. So in that case, Sn minus Sn minus 2 will be less than 0. That means Sn will be less than Sn minus 2. Then in that case, this sequence will be monotonic decreasing sequence. Now, if we look at the sequence of other terms, which is Sn minus 1 and Sn minus 3, there is this minus sign. So that means this Sn minus 1 minus Sn minus 3, it will be negative when Sn minus Sn minus 2, it is positive. So in that case, it will be negative. That means Sn minus 1 will be less than Sn minus 3. In that case, the sequence will be monotonic decreasing. And for the second case, when this value is negative, then Sn minus 1 minus Sn minus 3 will be greater than 0. That is, Sn minus 1 will be greater than Sn minus 3. Then the sequence will be monotonic increasing sequence. The two subsequences of odd terms and even terms, they will both be monotonic. And if sequence of odd is increasing, then sequence of even will be decreasing. Or if the sequence of odd is decreasing, then the sequence of even will be an increasing sequence. So we have proved that the sequence is bounded and the two subsequences of odd and even terms, they are monotone sequences. So if the sequence is bounded and monotone, then both the subsequences, they are convergent sequences. Now suppose sequence of odd, it converges to L1, and sequence of even, it converges to L2. Then from this condition we can write L1 equals S upon 1 plus L2 if n is odd, and L be L2 S upon 1 plus L1 if n is even. Now we compare these two, we'll get L1 plus L1 L2 will be equal to L2 plus L1 L2. Now L1 L2 will cancel, so we'll get L1 is equal to L2. So both the subsequences, subsequence of odd terms and subsequence of even terms, they'll converge to the same limit, say L. then the sequence will converge to this limit L, and we can write this L equals S upon 1 plus L, that is L square plus L minus S equals 0. So this limit point of the sequence, say L, it is a positive root of this equation, x square plus x minus S equals 0. And this is what we need to prove. Now the next thing that we'll study in sequences is Cauchy sequence. Now Cauchy sequences are also called as fundamental sequences. Now first we look at different definitions of Cauchy sequence. Now the first definition is a sequence Fn is said to be a Cauchy sequence if for any epsilon greater than 0 there exists a positive integer m such that Fn minus Fm mod is less than epsilon for all n greater than or equal to m. Now what we can do is we can write this definition in two equivalent forms, and the first form is for any epsilon greater than 0 there exists positive integer m such that Fm plus p minus Fm is less than epsilon for all p greater than 0. Or we can say a sequence Fn is said to be Cauchy sequence if for any given epsilon greater than 0 there exists positive integer m such that Fp minus Fq mod is less than epsilon for all pq greater than or equal to m. Now there are two theorems on Cauchy sequences that we need to know, and the first theorem is every Cauchy sequence is a bounded sequence, and the second theorem is Cauchy's convergence criteria, and we are more interested in this, and it says a sequence of real numbers is convergent if and only if it is a Cauchy sequence. So every Cauchy sequence, it is a convergent sequence and vice versa. Now let us take up an example. Say for example, we need to show that Fn, which is defined as minus 1 to the power n upon n, is a convergent sequence. Now we'll write mod of Fn minus Fm. Now Fn is minus 1 to the power n upon n, and then minus Fm is minus 1 to the power m upon m. Now this expression will always be less than or equal to 1 upon n plus 1 upon m, and if n is greater than m, then it will be less than 2 by m. Now Fn minus Fm, it is less than epsilon, then this m, it will be greater than 2 upon epsilon. So for any value of epsilon, however small it may be, we always get a value of m where n is always greater than m. That means the sequence Fn, it's a Cauchy sequence, and Cauchy convergence criteria says every Cauchy sequence is a convergent sequence. So the sequence, it is a convergent sequence. Now the next question is, using Cauchy's general principle of convergence, show that the sequence Fn is not convergent where Fn is 1 plus 1 by 2 plus 1 by 3 up to 1 by n. Now again we'll find mod Fn minus Fm. Now Fn will be 1 plus 1 by 2 plus 1 by 3 up to 1 by n minus 1 plus 1 by 2 up to 1 by m where n is greater than m. Now here 1 by 2, 1 by m will cancel. So we'll get this as 1 upon m plus 1 plus m plus 2 up to 1 by n. Now if we choose this n as 2m, we can write this as 1 upon m plus 1, 1 upon m plus 2, 1 upon 2m will be greater than 1 upon 2m, 1 upon 2m, m times. So it will always be greater than 1 by 2. So fn minus fm, it is greater than 1 by 2. Now this contradicts the condition of Cauchy's criteria. So the sequence is not convergent and it is not a Cauchy sequence. Now here the question is, using Cauchy's criterion of convergence, examine the convergence of sequence fn equals 1 plus 1 upon factorial 1 up to 1 upon factorial n. Now again we'll find mod of fn minus fm. Now it'll be again nothing but 1 upon factorial m plus 1, 1 upon factorial m plus 2 up to 1 upon factorial n. Now we know that factorial m plus 1, it will be greater than 2 to the power m. It will be less than or equal to 1 upon 2 to the power m plus 1 upon 2 to the power of m plus 1 up to 1 upon 2 to the power of n minus 1. Now this is nothing but a GP. We can write some of this GP as 1 upon 2 to the power m, 1 minus 1 upon 2 to the power of n minus m upon 1 minus 1 by 2, which is 1 upon 2 to the power of m minus 1 and 1 minus 1 upon 2 to the power of n minus m. Now it will be less than 1 upon 2 to the power of m minus 1. Now this is less than epsilon. So mod fn minus fm, it is less than epsilon when n is greater than m, and from here we can write 2 to the power of m minus 1, it will be greater than 1 upon epsilon, and if we take log both sides, we can write m is greater than 1 minus log epsilon, which means the sequence is a Cauchy sequence and therefore it is a convergent sequence. Now let us take another question, and it says, let yn be a sequence of real numbers given by y1, y2 and yn, and we need to show that this sequence is a convergent sequence using Cauchy's criterion. Now we find mod yn minus ym, it will be this mod 1 upon factorial 1 minus 1 upon factorial 2 minus 1 to the power n plus 1 upon factorial n, and then minus 1 upon factorial 1 minus 1 upon factorial 2 up to minus 1 to the power m plus 1 upon factorial m. Now it will be nothing but minus 1 to the power m plus 2 upon factorial m plus 1, and will continue up to minus 1 to the power n plus 1 upon factorial n. Now it will be less than 1 upon factorial m plus 1 up to 1 upon factorial n. Now it will be less than 1 upon 2 to the power m, 1 upon 2 to the power of m plus 1 up to 1 upon 2 to the power of n minus 1, and it will be less than 1 upon 2 to the power m, 1 upon 2 to the power of m plus 1 up to infinite, which is a upon 1 minus r, which is 1 upon 2 to the power of m minus 1. So for any n which is greater than m, yn minus ym, it is 1 upon 2 to the power of m minus 1. It will be less than epsilon. We can write 2 to the power of m minus 1. It will be greater than 1 upon epsilon, or m will be greater than 1 minus log epsilon. So this sequence, it is a Cauchy sequence and therefore it is a convergent sequence. Now we have to find limit of the sequence, we can write limit n tends to infinite yn will be simply 1 upon factorial 1 minus 1 upon factorial 2 plus 1 upon factorial 3. It will continue up to infinite. Now if we add 1 and subtract 1 and we take minus common, we'll get 1 minus 1 upon factorial 1 plus 1 upon factorial 2. Now this is nothing but it is expansion of e to the power minus 1. So this limiting value will be simply 1 minus 1 upon e. So this sequence, it converges to 1 minus 1 by e. Now there are some theorems on Cauchy sequences that says let fn and gn be two Cauchy sequences, then their sum will be a Cauchy sequence, their difference will also be a Cauchy sequence, their product will also be a Cauchy sequence, and if fn is unequal to 0, then 1 upon fn is also a Cauchy sequence. Now here the question is, we are given two sequences an and bn. Now this an is this summation k varies from 1 to n k upon k plus 1 whole square. Now what we'll do is we'll add 1 and subtract 1. We can write an as this summation k varies from 1 to n 1 upon k plus 1 and then minus summation k varies from 1 to n 1 upon k plus 1 square. Now we know that harmonic sequences 1 upon n to the power p, they are convergent if p is greater than 1 and they are divergent if p is less than or equal to 1. So for this one, summation 1 upon k plus 1, it is not a convergent sequence. So it is not a Cauchy sequence. And 1 upon k plus 1 square will be a Cauchy sequence. So this first sequence is not Cauchy and the second sequence is a Cauchy sequence. That means this an, it is not a Cauchy sequence. So this an, it is not a Cauchy sequence. Now what about bn? We can write this bn as this summation k varies from 0 to n ck and r to the power k, where mod ck is less than or equal to m. Now it will always be less than or equal to this summation mod ck r to the power k. Now it will be less than or equal to m into summation r to the power k. So it will be m 1 minus r to the power n upon 1 minus r, and since r lies between minus 1 and plus 1, so it will be less than m upon 1 minus r. Now this mod bn, it is less than m upon 1 minus r. So this sequence will be a Cauchy sequence. So answer to this question is an is not a Cauchy sequence, but bn is a Cauchy sequence, and that's your option C. Now we'll come to this squeeze theorem. It says, suppose we have three sequences x, y and z, and such that for all natural numbers xn is always less than or equal to yn, which is always less than or equal to zn, and if limit xn is equal to limit zn, then the sequence y will also be a convergent sequence and limit of y will be same as limit of x and z. Now let us take an example. Say for example it says, show that the sequence bn, which is 1 upon n plus 1 square plus 1 upon n plus 2 square up to 1 upon 2n square, it converges to 0. Now we know that n plus 1 square will be less than n plus 2 square and it will be less than n plus n square. Now if we take reciprocal, we can write 1 upon n plus 1 square will be greater than 1 upon n plus 2 square, and it will be greater than 1 upon 2n square. Now what we'll also do is we'll also write this is greater than n square, so it will be less than 1 upon n square. Now using these two extreme values, we can say that this bn, now for all these n terms, the smallest value is 1 upon 2n square. So it will always be greater than n upon 2n whole square, and its maximum value is 1 upon n plus 1 square, which is less than 1 upon n square. So it will be less than n upon n square. So every term of the sequence bn will be greater than 1 upon 4n and will be less than 1 upon n. Now we take this limit n tends to infinite. Now this limit is 0, this limit is 0. Then using squeeze theorem, we can say that the sequence bn, it is a convergent sequence and its limit of convergence is 0. And that is the answer to this question. Now here the question is, let an be a sequence of real numbers satisfying mod of an is less than or equal to 1 for all n. It has defined capital An as 1 upon n, a1 plus a2 plus an. Then we need to find this limit n tends to infinite under root n into an plus 1 minus an is equal to what? Now we find an plus 1 minus an will be simply 1 upon n plus 1 a1 plus a2 plus an plus 1 minus 1 by n a1 plus a2 plus an. Now we can simplify this as n times an plus 1 and then minus a1 minus a2 minus an upon n into n plus 1. Now we'll multiply it with under root n. We can write under root n an plus 1 minus an will be under root n into an plus 1 minus a1 minus a2 minus an upon n into n plus 1. Now this expression will always be less than or equal to under root of n and then n mod an plus 1 plus mod a1 plus mod a2 plus mod an upon n into n plus 1. Now mod an, it is less than or equal to 1. So this is less than n and this is 1 plus 1 plus 1 n. So we can write it will always be less than or equal to under root n into 2n upon n plus 1. Now here we will cancel this n with n. So this n an plus 1 minus an, it will be less than under root 2n upon n plus 1. Now we take this limit n tends to infinite. This limit here is 0. Now since we have taken this mod sign here, so it should be this mod value. So this value, it can never be less than 0. The only value possible in this case is 0. So this limit n tends to infinite n an plus 1 minus an, it will be 0, and that's your option A. Another theorem is, if fn and gn be two convergent sequences and if fn is less than or equal to gn, then limit fn will always be less than or equal to limit gn. And if fn and gn are two sequences such that mod fn is less than or equal to mod gn, then if limit gn is 0, then limit fn is also 0. Now let us take up an example. Say for example, Consider two real valued sequences xn and yn satisfying the condition that xn cube minus yn cube tends to 0 as n tends to infinite, then which of the following is correct? Now we'll write mod of xn cube minus yn cube, and it'll be equal to mod of xn minus yn into xn square plus yn square plus xn into yn. Now we'll multiply everything with 4. So we'll get 4xn square, 4yn square, and then 4xn yn. Now we can rewrite this as mod of xn minus yn, and here it will be mod of xn minus yn whole square plus 3 times xn plus yn whole square. Now it will always be greater than or equal to xn minus yn whole cube. So we can write xn minus yn cube will be less than or equal to 4 xn cube minus yn cube. And the question it says the value of this limit is 0. That means the value of this limit will also be 0. So as n tends to infinite, xn minus yn must tend to 0. So the answer to this question is as n tends to infinite, xn minus yn tends to 0, and that's your option A. Now in sequences, there are two more theorems, and the first one is monotone subsequence theorem, which says if x is a sequence of real numbers, then there exists a subsequence of x that is monotone. So every sequence of real number will always have a subsequence which is monotonic. And the next one is the Bolzano-Weierstrass theorem, and it says a bounded sequence of real number has a convergent subsequence. So if the sequence is bounded, then it will always have a subsequence which is convergent. So these are two theorems for subsequences. Now there are some theorems which you can use while solving some limits. Now it says if fn is a sequence such that limit n tends to infinite, fn plus 1 upon fn, it is equal to L, where mod L is less than 1, then limit n tends to infinite fn will be 0. And if this L is greater than 1, then in that case fn it diverges to infinity. Now let us take up an example. Say for example, show that this limit n tends to infinite 2 to the power minus n into n square, it is equal to 0. Now what we'll do is we'll write fn as 2 to the power minus n into n square. Now fn plus 1 upon fn will be 2 to the power of minus n plus 1 into n plus 1 square upon 2 to the power minus n into n square. Now 2 to the power minus n will cancel, so we can write this as n plus 1 square upon 2n square. Now we take this limit n tends to infinite. This limit will be simply 1 by 2, and which is less than 1. So if mod L it is less than 1, then this limit n tends to infinite fn will be 0. That means this limit n tends to infinite fn, which is 2 to the power minus n into n square, will be simply 0. And this is how we prove such questions. Now here the question is, show that this limit n tends to infinite m minus 1, m minus 2 up to m minus n plus 1 upon factorial n into x to the power n is equal to 0 if mod x is less than 1. Now suppose this is fn. We'll find this limit n tends to infinite fn plus 1 upon fn. Now fn plus 1 will be this limit n tends to infinite m minus 1 m minus n upon factorial n plus 1 into x to the power of n plus 1 upon m minus 1 m minus n plus 1 upon factorial n. Now here all these terms, they'll cancel. So what we'll get is, we'll get this as limit n tends to infinite m minus n, here we'll also have x to the power n into x upon n plus 1. And if we divide it by n, we can write this as limit n tends to infinite m by n minus 1 into x upon 1 plus 1 by n, which is nothing but minus x. Now this is your L. Now value of this limit will be 0 if mod L it is less than 1. That means mod of minus x will be less than 1, or we can say when mod of x is less than 1, which is what we need to prove. Now there are two very important and simple theorems in limits, which are Cauchy theorems on limits. Now the first theorem says if limit an equals to a and bn is average of all these ai's, then limit of b is same as limit of a. And the second theorem says if an is a positive number, then for all n, this limit n tends to infinite an to the power 1 by n will be same as this limit n tends to infinite an plus 1 upon an. Now we generally use these theorems to simplify problems in limits. Let us take up an example. Say for example, the question is, show that this limit n tends to infinite 1 upon under root n square plus 1 plus 1 upon under root n square plus 2 up to 1 upon under root n square plus n, and this is equal to 1. Now generally we solve this question using sandwich theorem or squeeze play theorem. Now here we are going to solve this question using Cauchy's theorem on limits. So what we'll do is we'll write this as limit n tends to infinite 1 by n upon under root of n square plus 1 plus n upon under root of n square plus 2 up to n upon under root of n square plus n. Now this limit is of the form limit n tends to infinite 1 by n a1 plus a2 plus an. Now Cauchy's first theorem says this limit, it is equal to this limit n tends to infinite an. So all we need to do is we need to solve this limit n tends to infinite. Now what's an? An is n upon under root of n square plus n, and this limit is nothing but 1. So value of this limit is simply 1. Now here the question is, we need to show that this limit 1 by n, 1 plus 2 to the power 1 by 2, 3 to the power 1 by 3 plus n to the power 1 by n is equal to 1. Now using Cauchy's theorem, we can say that this limit, which is 1 by n a1 plus a2 plus a3 plus an, is equal to limit n tends to infinite an, and an in this case is n to the power 1 by n. Now we can write this as limit n tends to infinite e to the power log n to the power 1 by n. So it will be e to the power this limit n tends to infinite log n by n. Now this is log infinite
upon infinite. So it is infinity upon infinity form. We can use L'Hopital's rule. We can write e to the power this limit n tends to infinite, and it'll be 1 by n upon 1. So it'll be simply e to the power 0, which is 1. So the value of this limit is nothing but 1. Now here the question is, evaluate this limit. Now we'll take this as y, and if we take log, we can write log y equals limit n tends to infinite 1 by n log 2 upon 1 plus log 3 upon 2 square plus log n plus 1 upon n whole to the power n. Now we'll use Cauchy's first theorem. We can write log y equals this limit n tends to infinite an, and an in this case is log n plus 1 upon n whole to the power n. Now this is log y, and it'll be this log, and this is standard limit 1 plus 1 by n to the power n when n tends to infinite, and this is nothing but e. Log e is 1. If we take anti-log, value of y is simply e. So value of this limit is nothing but e. And the second theorem says, if an is a positive number, then for all n, this limit n tends to infinite an to the power 1 by n will be same as this limit n tends to infinite an plus 1 upon an. Now here in this question, we need to find limit of the sequences an to the power 1 by n and bn to the power 1 by n. Now Cauchy's second theorem says this limit n tends to infinite an to the power 1 by n is same as limit n tends to infinite an plus 1 upon an. So for this first one, if we have to calculate this limit will be equal to limit n tends to infinite an plus 1 upon an. Now limit n tends to infinite, what's an plus 1? An plus 1 will be factorial 3n plus 3 upon factorial n plus 1 cube upon an, and an is factorial 3n, and here will be factorial n cube. Now we can write this as limit n tends to infinite. Now it will be 3n plus 3 into 3n plus 2, 3n plus 1. Now factorial 3n will cancel upon n plus 1 whole cube. Now this is infinite limit. Highest power of n is 3. So the coefficient of highest power of n in the numerator is 27 and the denominator it is 1. So value of this limit will be simply 27. So answer to this first one is 27. Now again for the second one, we can write this as limit n tends to infinite bn plus 1 upon bn, and LB this limit n tends to infinite. Now bn plus 1 is n plus 1 to the power n plus 1 upon n plus 2 n plus 3 up to 2n plus 1 2n plus 2 divided by bn, and bn is n to the power n upon n plus 1 n plus 2 up to 2n. Now n plus 2 n plus 3 up to 2n will cancel. Now we can write this as this limit n tends to infinite n plus 1 to the power n plus 2 upon n to the power n 2n plus 1 and 2 into n plus 1. We'll cancel this n plus 1 once. So you'll get n plus 1 to the power n plus 1. Now we can also write this as limit n tends to infinite n plus 1 upon 2n plus 1 into 1 plus 1 upon n to the power n. And we also have this 2 here. Now we take this limit, this part will be simply 1 by 4, and then this is 1 to the power infinite form, and this is standard limit, its value is e. So limit of the sequence will be simply e by 4.
Now question number 7 is, let x naught greater than 0 and xn be defined recursively by xn equals under root of 6 plus xn minus 1, where n is greater than or equal to 1, then this limit n tends to infinite xn is. Now we can write this xn as under root of 6 plus xn minus 1. We can write this as xn square, it will be 6 plus xn minus 1. Now what we'll do is we'll subtract xn minus 1 square from it. So it will be xn square minus xn minus 1 whole square, and if we take minus common here, we'll get xn minus 1 square minus xn minus 1 minus 6, and if we factorize it, we can write this as xn minus 1 minus 3 and xn minus 1 plus 2. Now here critical points are 3n minus 2, and since x naught is greater than 0, we'll take two cases. Case 1, if x naught is less than 3, and case 2, if x naught is greater than 3. Now if x naught is less than 3, then if we add 6, we'll write 6 plus x naught will be less than 9, that is under root of 6 plus x naught will be less than 3. We can write x1 will be less than 3, and using same iteration we can write xn will be less than 3. Then in that case this function will be bounded above. Now if xn is less than 3, then this value will be negative, this value will be positive, and then we have this minus sign here, so it will be minus and minus plus. So we can write xn square minus xn minus 1 square, and it will be greater than 0, that is xn is greater than xn minus 1, that is the sequence is monotonic increasing. So if the sequence is bounded above and increasing, that means this sequence it is going to converge. Now what about the second case? And the second case, when x naught is greater than 3, if we add 6, we'll get 6 plus x naught will be greater than 9 under root of 6 plus x naught will be greater than 3, that is x1 is greater than 3. If we add 6, again if we take square root, we'll get x2 greater than 3. So from here we'll get this xn, it should be greater than 3. So in this case it is bounded below. Now if xn is greater than 3, then this expression will be positive, this is also positive, and here we have this minus sign. So we'll get xn square minus xn minus 1 square, it should be less than 0, that is xn, it should be less than xn minus 1. That means this sequence is now a decreasing sequence. So if the sequence is bounded below and monotonic decreasing, that means the sequence it will converge. Now what about if x naught is 3? If x naught is 3, then this sequence will be a constant sequence, and we know that a constant sequence is a convergent sequence. So this sequence will be convergent for all the possible values of x naught. Now we'll need to find this limit n tends to infinite xn. For that what we'll do is we'll take this limit n tends to infinite both sides. Now suppose this limit is L, so we can write L equals under root of 6 plus L, that is L square minus L minus 6 equals 0. That is, the value of L is either 3 or the value of L is minus 2. Now since this sequence, it contains positive terms, its limit point cannot be negative. So for this sequence, the value of this limit is simply 3. So this limit n tends to infinite xn will be 3, and which is none of the above, option D. Now here the question is, let a1 equals 1 and an equals n into an minus 1 plus 1 for n equals 2, 3, 4. Define Pn as 1 plus 1 upon a1 into 1 plus 1 upon a2 up to 1 plus 1 upon an. Then we need to find this limit n tends to infinite Pn. Now we can write this Pn as a1 plus 1 upon a1, a2 plus 1 upon a2, and in the same way it goes up to an plus 1 upon an. Now from this recurring relation we can say that an minus 1 plus 1 upon an, it is equal to 1 upon n. So we can write this as 1 upon a1 and then a1 plus 1 upon a2 into a2 plus 1 upon a3, and it goes all the way up to an minus 1 plus 1 upon an into an plus 1. Now this is 1 by 2, this is 1 by 3, and this is 1 by n. So we can write this as 1 upon factorial n an plus 1 upon a1. Now we are also given that a1 is 1. So we can write this as 1 plus an upon factorial n. Now this is 1 upon factorial n plus an upon factorial n. Now an upon n is an minus 1 plus 1. So we can write an upon n is 1 plus an minus 1. So we can also write this as 1 upon factorial n plus, and this is 1 plus an minus 1 upon factorial n minus 1, which is 1 upon factorial n plus 1 upon factorial n minus 1. Now if we continue in the same fashion, in the end we'll get 1 upon factorial n plus 1 upon factorial n minus 1 plus a2 upon factorial 2. We can also write this as 1 upon factorial n plus 1 upon factorial n minus 1, 1 upon factorial 2 plus, now a2 upon 2 is 1 plus a1, and a1 is 1. So it will be 1 plus 1 upon 1. So that's your Pn. Now if we take this limit n tends to infinite Pn, it will be 1 plus 1 upon factorial 1 plus 1 upon factorial 2, and this series, it goes all the way up to infinite. It is nothing but e. So the value of this limit n tends to infinite Pn will be simply e, and that's your option B.